The outline on slide 116 shows that we have now come to the last section of the Webtalk, statistical methodology. And we're going to start with talking about posterior probabilities and most likely class for 3-step and BCH, where we take into account the measurement error, or the classification error that is part of the MLC variable. And this really expands on the brief introduction to this topic that we provided on slides 7 and 8. So this table here looks familiar to you from that part of the talk. We show an example of 6 individuals and 3 latent classes, and the posterior probabilities are given for each individual and each latent class through the cprob option of the save data command. And the most likely class is bolded. So for individual 1, class 1 is the most likely, and for individual 4, class 4 is the most likely, just barely. Individual 6, class 1 is the most likely. We can give a summary of this in a table with average class probabilities for most likely class as rows and class as column, where n is the MLC variable here, the nominal variable. So that is the top table of the 3 tables that we showed on slide 39 from the Mplus output. And that top table is just an interim step in the computation of what we really are interested in, the table of n given c instead of c given n. And n given c, that reverse probability, can be computed using Bayes' theorem, which is really just a manipulation of probabilities in a very straightforward fashion. And that table, information in that table, is used by both 3-step and BCH in capturing the measurement error or classification error in the most likely class variable. So top left here, we repeat the table that we just looked at. And now we're going to try to figure out what the interim table, what I refer to as the top table of slide 39, how it is actually computed. Probability of c given n. So let's take our time with this. So first we have n equals 1, c equals 1. So we look at which individuals are classified into class 1 when the true class is 1. So that's individual 1 and individual 6. And the probability that c equals 1, that we're in first column, is then the average of those 2 probabilities. So 0.5 plus 0.5 divided by 2. For the people who have n equals 1 as the most likely class, namely individual 1 and 6, what's the probability for c equals 2? Well, then you look at the c equals 2 column for those variables, 0.3 and 0.2, and take the average of that, of those 2. For c equals 3 for the same people, being in the third column, as probability 0.2 for individual 1 and 0.3 for individual 6. So you put that into the average here over the 2. For n equals 2, you have 3 individuals who have most likely class being 2. So you have, for those people, c equals 1 is 0.1, 0.3, 0.3. So you take the average of those 3. For c equals 2, well, then you are in the column with the most likely class. So you have 0.6, 0.4, 0.7. For c equals 3 for those same 3 people, 0.3, 0.3, 0.0, 0.3, 0.3, 0.0. And for the individuals who are most likely class as 3, that's only one individual. So C equals 1 class membership then has probability 0.1. So you have 0.1, it's only 1. And for class 2, 0.1 again. And for class 3, it's 0.8 divided by 1. So here you have those probabilities computed for the individuals. And then you can summarize that in the table at the bottom here. So the first row is simply, so n equals 1, that's the first 3 computations. So 0.5 divided by 2 is 0.5. 0.3 plus 0.2 divided by 2 is 0.25. Same for the third one, 0.25, etc. down to the last row where you have 0.1, 0.1, 0.8, 0.1, 0.1, 0.8. So this table bottom here just summarizes what we had at top right. So turning to slide 119, let's see how we can get to the probability table for n given C, obtained via the Bayes theorem. So it looks like this: n given C equals C given n, where C given n was obtained at the bottom of the previous slide. If you multiply that by the probability of n, that variable having different values, and divide it by the probability of C having different values, you get the probability of n given C. So it may look mysterious, but it's very simple if you consider multiplying this denominator up on the left-hand side, and then it says probability of n given C times the probability of C. So that's the joint probability of n and C. And on the right-hand side, you say the same thing. C given n times probability of n is the joint probability of C and n. So you can check that you have an equivalence here between the left-hand side and the right-hand side. So we already computed C given n. So now we need to figure out what probability of n and probability of C are. Probability of n equals 1 through 3 here. Well, that's fairly easy to get. If you go back one slide, probability of n being 1 is, you have the 0.5 and 0.5 here. So you have 2 of them being 1, so 2 out of 6. And for here we have 3 out of 6, and then 1 out of 6. 3 out of 6, 1 out of 6. So that's easy to compute. Probability of C, well, that's the probabilities down here, the marginal probabilities of the classes. So those 2 components that we add are very simple. So now we just have to multiply it all together. The hard part was computing the first term here. So now we multiply them together, and at the bottom then you see how we piece it together. So you recognize the 2 divided by 6 and 0.30 here. And these values, 0.5, 0.25, 0.25, they come from the first row of the table on the previous slide, 0.5, 0.25, 0.25. So rows and columns are transposed. So the next column, 0.3, 23, 0.57, 0.20 is this row. And the last column, 0.10, 0.10, 0.8 is the last row down here. So that's what you get, putting the 3 pieces together. And if you compute these values, this is still working with the example of the 6 individuals. You can make a lot of material out of only 6 people. Then you get this table on slide 120, which we have looked at before, and corresponds to the Mplus output, the so-called middle table on slide 39 for a regular analysis. So this is probability of n given c. Why are we interested in that? Well, first of all, the output in Mplus refers to this table as classification probabilities for the most likely latent class membership column by latent class row. Why are we interested in that? Well, that table, it really represents a multinomial regression of an observed indicator n on a latent variable c. So compare that with factor analysis. So this is n is like a factor analysis indicator, and we're seeing it as a measurement error prone indicator of latent class membership. The table shows, as I say in the last bullet, and we've said before, MLC is not a perfect indicator of latent class membership. We don't have 1, 0, 0, but it can be seen as having measurement error or classification error. Now, what do we do with that then? Well, we use that in two ways, that table information. And for 3-step, we use it as follows, and the next slide shows how we use it for BCH. So the measurement error is translated into logits for each latent class and category of the nominal variable n. And we do that because the influence of C on n in our model is expressed by logits. So we want to translate these probabilities into logits. Logit for n given C divided by n last class given C. So we looked at a certain value for n, certain category for n, compared to the last category for n. So let's take an example. If you look at the table on the right here, minus 0.48, how do we get that? Well, minus 0.48 is the log of 0.26 divided by 0.42. So that's n equals 1 for the last class, n equals 1 for the last class, the last row, divided by n equals last, the third, for that same person, for that same class 3. 26 divided by 42, the log of that is minus 0.48. And we see then that the diagonal values are the highest, as we would expect. The higher they are, they come from these values, on the diagonal, divided by the last class. So the higher they are, the better the classification, the smaller the measurement error. So 0 is higher than the negative values here, so that's true for all three. So we make a correction for this most likely class measurement error in the last step analysis, where the nominal n variable is added to the analysis variables and given these fixed logits. So they come from the Pn given C table, which comes from the posterior probabilities for each individual. Now for BCH on slide 122, it's a little bit more involved, but Jerome Vermont in his 2010 paper has made a nice summary of it, or expansion of the BCH approach, because the BCH comes from the three authors of the original article from 2004, Bolk, Kroon, and Hagenars. He considers BCH for an LCA where the full model adds covariates. So the extra variables are the covariates X. So, and he considers three matrices, E, A, and D. So E is a probability of n assuming a value being in a certain class, most likely class, given the covariates for individual I. So that's a matrix with the rows, a number of people, and columns being the different categories of n, the number of classes. So that is a biased relationship with x. It's most likely class regressed on x. It's not the same as C on x, the true unbiased relationship with x, which is given in matrix A. And from that then, I can also add a matrix D, probability of n equals n given C equals C, the measurement error in most likely class, which we just discussed. And the key to understanding this is that the probability of n given x, the first one, E, is equal to a product, sum over the product of C given x and n given C. So C given x, true unbiased relationship, and the measurement error relationship. And we sum over C, which is the columns of A, and it corresponds to the row of E. No, sorry, rows of D, the rows of D. And summing over that is actually then a matrix product, A times D. So that the E matrix, the biased relationship, is equal to A, the true relationship, times the measurement error matrix. So we note that E is equal to A times D, and by matrix algebra you can multiply it by D inverted on both sides, and you get that A, the true relationship, is equal to the biased relationship times the inverse of the measurement error matrix. So we take the inverse of that measurement error matrix that we computed, and thereby we correct the biased relationship of E, n given x, using the inverse of D, the measurement error matrix, as weights in the regression, in the E regression, n on x. So we adjust the n on x for the unreliability in n using this measurement error matrix, probability of n given C. The matrix A then contains the BCH weights that vary across individuals. We see up here that A has rows corresponding to individuals I. So those are the weights. On slide 123, the outline points to the statistical topic of missing data on a binary covariate. And we are now in the context of using maximum likelihood. And consider an example with a regression of y on two x variables, x1 and x2, where x1 is binary with missing data, and the x's are brought into the model using with. So we have y on x1, x2, and x1 with x2, like we have done in the section with missing data on covariates. By saying with, our x's are now treated as dependent variables in Mplus, so we're estimating their whole distribution, parameters of their distribution. Now x1 is not on the categorical list because ML cannot handle with involving categorical variables. There's no parameterization for it. So we are ignoring that x1 is categorical, and what happens then in the EM algorithm, expectation maximization algorithm that ML uses? Well, the expectation step for the x's does not recognize that x1 is binary, but uses a continuous variable normality assumption for it, so that expectations for continuous, not binary variables are produced. And the M step, the maximization step, then regresses y on those continuous x1 variables, except for the non-missing x1 observations, which are kept as binary. So that's an approximation that's being made. But there is missing data literature that indicates that this approximation is sufficiently good to not produce an important bias in the regression. And I give some references here from Joe Schaefer's book, and Demirtas has an article, and those references are given in our book, the Regression and Mediation Analysis book from 2016. So I talk about those matters, and I do simulation studies that support that there is not an important bias by making this approximation. But you should be aware of it. And on slide 125, you can think of an alternative, the Bayes alternative. Chapter 10 of this 2016 regression mediation book shows that Bayes can handle this case better because it allows x1 to be put on the categorical list and allows using with. It has parameterization for that, namely a probit, underlying normality parameterization. And the simulations that I did in that book chapter show that this gives slightly better results than ignoring that x1 is binary when you have a lot of missing data and when the missing data is not missing at random. So it's not MAR, but NMAR. But we don't have this approach available yet for mixture models in Mplus because it requires being able to do a regression of C on x1 with missing x1. But if it proves important to include, we will add that later on. Turning then to the next statistical topic, why class-varying regression can be considered as an interaction. Slide 127 give you a reminder of interaction thinking with linear regression as a start. So say that you have observed covariates x and c, so pretending that our latent class variable c is observed for a second. So you have y regressed on x and c and their interaction. You have an intercept as usual. So you have these B1 and B2 and B3 coefficients of primary interest. Now you can reshuffle that equation so that this term and this term get put into a summary term where you pull out x multiplying B1 is that term, x multiplying B3 times c is that term. And then you have the effect of c here. So B1 and B2 are the main effects of x and c respectively, and B3 is the interaction effect, where B1 plus B3 times c is called a moderator function. C moderates the impact of x on y. And if you evaluate that at a specific c value, we call that a simple slope. So we'll focus on the four parameters of the model A, B1, B2, and B3. So how does this translate to the mixture case then? Well, repeating what we saw on the previous slide, interaction with mixtures where C is a latent class variable is what we want to consider now. So say that you have two classes, and say that C is scored as a 0, 1 variable, like a dummy variable. With more classes, there would be more dummy variables. So in line with equation 2, where we write it with this interaction term here, B1 is the effect of x on y for the first class, because C is 0 for the first class, so it's B1 times x. So B1 is the effect of x on y for the first class, and B1 plus B3 is the effect of x on y for the second class, where c equals 1. So the interaction is the difference in effects, that is B3. So B3 is the interaction, just like before. In the mixture notation, we write it as y equals a, an intercept that is class specific, so subscript c, and a slope on x that is class specific with subscript c again. So this model has 4 parameters, just like with linear regression. We have 2 a's and 2 b's. And in the no interaction case, and that we've looked at a lot, we have a b without the subscript, and only a varies across the classes. And the class invariant b, class invariant regression, say on of distal outcomes on covariates, allows the effect of c on y to be summarized by the simply by the intercepts ac. With an interaction that is bc, the effect of c can no longer be summarized by the intercepts alone. So again, I make that comparison with the analysis of covariance that I mentioned in the main part of the talk. All right, so then turning back to the outline, let's take a look at an overview of Monte Carlo studies, which is useful because you don't learn that much from a single data set. But when you generate data according to various models, you learn quite a lot. So let's take a look at slide 130. And there may be more in Monte Carlo studies that I have missed and more that are coming all the time. But here are the key ones so far here in July of 2025. C on X, regression of C on X. And for that part of the model, Jerome Vermont in his 2010 paper studied 3-step compared to BCH. And they're approximately equal in terms of bias. 3-step has a bit less variability than BCH. Bach and Kua, in their 2018 article, show that 2-step analysis can be slightly better than 3-step and approximately equal to BCH in terms of bias. But 2-step has less variability than BCH. So one could conclude then from those 2 studies that maybe one should choose 2-step for C on X. But the differences are fairly small, I would say, compared to, say, 3-step or BCH. We have the WebNote 21 where we looked at random intercept latent transition analysis, so more than one latent class variable, where we found that 2-step did better than BCH. So maybe 2-step is slightly favored in the C on X context. Let's take a look at the Y on X context on slide 131. Bach and Kua's article again claim that 2-step, 3-step BCH are pretty much the same, except for when you have very low entropy. Low entropy, the multi-step methods don't work that well, generally speaking. You want to have moderate to high entropy. When you have very high entropy, you don't even need them. So there is that sweet spot, moderate entropies, where they work well. Now, 2-step and 3-step have slightly less variability than BCH for Y on X. But Y on X with unequal Y variances across classes, if you generate the data that way, you can see that BCH has less bias than 3-step. 3-step allowing unequal variances is the best. Now, Y on X with non-normal Y within class, which is a little bit like what we had for the ASB real data example, antisocial behavior. Bach and Vermont pointed to BCH as having less bias than 3-step. And Bach and Kua said that BCH is best, 2-step equals 3-step pretty much. And we in WebNote 21 found BCH to be the best, 2-step bad, 3-step very bad. So even though 2-step and 3-step have slightly less variability than BCH, maybe BCH is safer bet than, say, two-step when you consider y on x. Slide 132, then we take a look at the case where you have C on x with missing data on a binary x. So that gets close to what we've been concerned with here for missing data on covariates, and my discussion about x1 being binary and ML being an approximate method. So we have DePaoli and Ja and Visser in 2025 only looked at three-step and found they created data with missing completely at random and missing at random MAR as a function of a U indicator. So they had the missingness was a function of a latent class indicator rather than what we did, where missing data on some x's was a function of another x with no missing data. So you can argue about which is most realistic in real life. It's hard to say. They found that FIML, that is maximum likelihood, approximately equal to Bayes and approximately equal to multiple imputation. And no discernible bias was found for FIML, ML, or Bayes for C on X when X is binary with missing data. So that supports the notion that the approximation treating the binary X as continuous normal is all right. FIML uses width among the x's, ignoring that x is binary, and the way they did Bayes was the same way. They used the Mplus default to diffuse priors. If you use, that is, uninformative priors, which is Mplus default. Using informative priors, of course, reduce the mean square error if you have any information about what is a reasonable prior, which you often don't have, but sometimes you do. Multiple imputation using of x's missing on x using x and u information, so latent class information, which is what we did. We also used distal outcome information, so that's a little bit different. Some bias with a high degree of missingness was found with strong effect when you have strong effects of x on C. All right. Coming to the last statistical topic then, how did we generate the data, the distal.dat? So slide 134 then shows the reasoning here, where we use in Mplus we use a logistic regression specification. The dependent variable is missing or not missing for the probability of missing on x1 and x2 as a function of x3. And you see that x1 and x2 is regressed on x3. So x3 influences the missingness of x1 and x2. This is the MAR part. Whereas in bracket here you have the intercepts, and if you only had the brackets, you only had the intercept and not the next line, then you would have MCAR, missing completely at random. But we were more interested in the MAR case. At the mean of 0 for x3 here, the logit intercept of -1.5 translates to a probability of missing on x1 and x2 of the logit to probability transformation here, 1 divided 1 plus e to the minus logit, minus become plus, 0.18. So that's at the specific value of 0 for x3. One standard deviation above the mean of x3, the logit of -1.5 plus 0.4 translates to a probability of missing 0.25. So you have a range of missing data probabilities across the range of x3. x3 being a continuous normal variable. Now, the leading individuals with missing on one or more of the x1, x2 covariates, which is listwise deletion, creates a sample size loss of 33%, which we saw earlier. So slide 135 and 136 shows you the input for Monte Carlo generation of our LCA data, where we create and save and create and save the distal.dat. So here's a list of variable specifications: x1 binary with missing, x2 continuous missing, x3 continuous not missing, y1 continuous missing, y2 binary missing, y3 ordinal not missing. Exactly what we have used in the main part of the talk. So you generate 3 classes, and they are, the categorical variables are binary, 1 threshold, except for y3, which has 2 thresholds. It's ordinal 3 category. And you specify categorical variables here and missing, which variables are missing, and then you have a model missing command, which we just looked at, to which we add missing on y as well. So the missing on y here is missing completely at random. There's no regression on another observed variable. So it's type equals mixture, algorithm equals integration, integration equals Monte Carlo, like we talked about before. And the model population then specifies the exact values for each parameter that we have. Continuing on slide 136, where the thresholds here are the values that give the feature of classes that we have looked at. And then you have the model command, which we copy from the model population command to check that everything comes out okay. So there you have it. Now on slide 137, we analyze these data knowing the missing data mechanism. So it's a correct full model specified as the data were generated. So now we're pretending that we have real data. That's the data set we created. And we're just checking that everything comes out okay by analyzing it, not in a Monte Carlo study, but in sort of a real data study. So the specifications are the same here. Now we have to search for the solution, and the algorithmic stuff is the same. And we have then the specification x1 and x2 on x3. So that is specifying the missing data mechanism the correct way. We don't have x1 through x3 with x1 through x3 like we did before, but we have it in this fashion instead. If you and a variation on this theme is then that we ignore the missing data mechanism, we pretend that we don't know it, and that is the case. Actually, we don't know it in real data, and then this slide would have the with statement instead, and then this slide would represent a one-step analysis, which we showed in earlier slides. All right, and with that we have reached the reference section and the end of this Webtalk 8. Thank you for your attention.